Did any trouble when you take simulation with Proteus, right? Hello? Can you hear me, guys?
Yes, sir.
Okay. Okay, how about the simulation on Proteus? Can you this it well? Any question?
CB anh nằm đâu? CB mấy anh này nằm đâu?
Kia,
CB mấy anh này?
CB nó nằm bên này. Okay. Then let me review the test that we study on Latwis, and we have studied about RTD, and if we want to reach to the sensor signal, that is the RTD value that will be depend on the temperature. And if we want to reach the signal, take its output. And this is Vs plus and Vs minus. And if we want to take this output, we need to apply the current I. The current I into the sensor, and that's here is the ground, and here is the ground, and then it's 0 voltage. Okay, and there is some of W here, W. Little. It means that Y resistance. Okay, and in this case, we need to take current, and there are some methods to make the current. The first one, we can apply voltage. when we apply voltage. And in this case, we can apply voltage by using once here and voltage VCC apply here, and then the current I can be calculated by a quick equation VCC divided by R1 plus plus RTD. In this case, we can add some more to RW in this case. Okay. And in this case, when RTD is changed, and then the I will be changed too. Will be changed. And in this case, it will make a little it will be difficult to take a calculation. Because it depends on the current, and the current is changed by the change of the value of RTD. The best way is that we using we use the current source. And the current source will be constant. The current source is constant. Okay. When the current source is constant, it will be have to easier to take the linear relationship. In this case, because of the non-linear. Non-linear relationship. Non-linear. And if I is a constant, in this case, so that the value of the voltage Vs equal to I multiplied by Td, and then it will be linear. It will be linear to os I multiply I0 and 1 plus alpha t, and this is a linear relationship. Okay, and it will be easier for us to take a calculation for t. Okay, and that's how we take a current source. Current source. And how can we measure? We can take a Google search. there are some methods to make a current source. And in this case, we can test using op amp. When using op amp, we can take a current source like this. Okay, we take voltage here, op amp here, and then we can take the reference V0 here, and then here resistance here, and this will take a ground here, take a ground here, and then we can have R and R0. Okay, everyone is R1. And in this case, the current source is the current source. The current is constant. I is constant equal to V0 divided by R1. Okay, and in this case, the current is always constant. Okay, and that's it independently to the value of RTD. When we use at RTD, the value of current is not depend on value of RTD, and this one help us to easier for take a calculation. Okay, and if we choose I is equal to, I assume that 2 milliampere. 2 milliampere. And then the R1 value will be V0 divided by R1 divided by I divided by I. And in this case, I can select this one equal to 5 volts, and no, this one is too high. Okay, and in this case I will choose it at 0.5 volts divided by 250 ohm. 250 ohm.
Okay, so now we begin with the lead controller first. Remember, we are in frequency domain.
Is that correct?
And we also have two procedures, one for lead controller and one for lab controller. And now we'll try to explain why is that.
Divide by 500. Okay.
Okay, so let's review the procedure.
R1.
Here we have
500 ohm and
a step, and the last step is to check if all the requirement has been satisfied. Okay, so at the first step we determine KC,
and that's
based on studies that arrow requirement. Okay, and normally we have 3 requirements like this. Normally, one related to arrow requirement, and one for phase margin and one for gain margin.
Okay, in this case,
we will use these 2 requirements to design our controller, and then we check if our design controller satisfy this requirement. Okay.
VF plus can be
So
calculate
after
by,
having KC from the first step, we multiply KC
around
with the original
equal
system
to
to obtain Z sub 1. And now
I
we did a Bode
multiply by
diagram of Z sub 1. Remember,
plus
Z sub 1, not Z of S. Okay.
URW.
And for step 3 and step 4, we determine the gain crossover frequency
That one
and the phase margin. You should be very familiar with these steps. And then we determine the necessary phase lead angle we want to add it to our system based on that. This is the requirement, is the current value, and this some value for threshold. Okay, so we get this work,
okay, that is
and we compute alpha using this formula and determine the new crossover frequency
VS
using this condition. Now we know the right hand side, right? So based on the
RTD
Bode diagram here,
equal to
we can determine the new frequency such that it satisfies. And finally, we can compute the constant T based on alpha and then the new crossover frequency.
And
nhớ không các bạn? So now we need to explain. So and now take a look at this one first. The blue lines are for original system. The green lines are for your controller, the lead controller. You see that the angle here from way positive, right? And the red lines are for the final system. Okay. So at the beginning, your crossover frequency is this one. Okay. And your phase margin is this value. Okay. So now we determine the new crossover frequency. This is the new crossover frequency. And
that's
this one.
We can take a relationship.
Is the lead angle we add it to the system. So this one should be
minus VS.
The new phase margin
equal to I0 alpha T. And in this case, we can take value of T equal to VST minus VS0 divide by I0 alpha and G value on the pre value is now. And then it will be easy to take the value of T and the value of T linear relationship to VS. Okay, it will be the linear, but the other one cannot be linear. Okay, and if I equal to 2 milliampere, I0 equal to 100 ohm, and alpha equal to 0.00385. Here the value, and we can take calculation for the one like this. Okay. Okay, that is the first one. And the next one is how can we reach this as how can we reach this? In this case, we have studied that we're using IDC. IDC. That is ID. It means that I analog to digital converter. Okay, analog to digital converter, and we have studied that and IDC value. Okay, takes IDC value equal to Vs divided by V's reference multiplied by 2 power n minus 1. And it depends on number of bits of IDC. And then with the microcontroller, okay, 80 mega chip MCU, then n equal to 10, and then the value equal to 1023. Okay, and then if we get this, we can take a calculation for Vs, and then Vs equal to Vs equal to IDC value multiplied by this is F and divide by 1023 and 1023, and that we can take a calculation for T which is 1. Okay, and with relationship with IDC, this one is the value of T at this. Okay, this is the value. Okay, and at Vs 0, at 0 Celsius degree, and we can test with IDC value at 0 multiplied by with R is F divided by 1023. Okay, it's a linear relationship, and then okay, at T. Okay. Okay, and we can take calculation directly. At V at 0 Celsius degree, and Vs equal to Vs 0, and then the value of IDC value 0. and the value of IDC with 0 equal to Vs 0 multiply by V VIZ and at this and we can get value of IDC value at this equal to Vs multiplied by 1000 okay, as it will be linear IDC vs IDC value okay, and that's the add value of Tmax value, and we will have IDC value of Tmax at Tmax. Okay, and then we can take a calculation as this T minus 0 centigrade degrees divided by T mass minus 0 centigrade degrees. It will be equal to this value IDC minus IDC value at 0 divided by IDC value mass divided by minus IDC value at 0. Okay, and then we can take calculation directly from this one without needing anything. Okay, and then now we come back to the simulation first. Okay, let's we again return with this one. Take cell S. Okay, and as we can test any circuit here. Okay, sorry. Okay, in this case, I will test okay, and okay, this was and how to apply the current. Okay, and then we need one of amp to take the current source. Here was of amp, and okay, and this was will be reference voltage, and I can apply the one stroke here. DC shock. Okay, and this case I will take it at 1 volt, 1 volt, and it will now we take a resistance. Okay, resistance here, and the value is 500 ohm, and the taking ground. Okay. And as the current will be take account to request, and then this is applied directly to request. Okay, and the other one. Okay, E minus will move to this place. Okay, and then here is the current source. Okay, and that we will apply power for request. Power, take power. Okay, V plus and V minus. In this case, I will apply for V plus 10 volt, and V minus 10 depends. But request. Okay, and then we can test a simulation. The value of current, I will check. Okay. Current. Okay. No, I saw. Okay. And take probe to measure. Okay, take a measurement here, and then we can have the voltage. Voltage indicate is around 1 volt, 1 volt here. And Vs plus, Vs minus. Okay, and at this case we can check for the voltage output. The voltage output in this case is correct or not. Okay, as we know that the current through this one is 2 milliampere, 100 ohm. Okay, in this case I will reduce at 20. Okay, this is 200 volts. 0 volt. And how much is the voltage? I don't know, correct or not? Let's check again. Okay, in this case, it's 1 volt here, 1 volt here. Vs minus, Vs plus. Okay, And then we take a calculation for request. Calculation. Okay. One more. Okay. And then we have a current I equal to uh, 2 milliampere. It means that 0.002. Let's see the current and value of RTD will be equal to okay, temperature first, RTD value, and the value is 0, 10, 20. Okay, and then I increase. Okay, assume that we can take maximum for around 200 centigrade degrees. Okay, and that's the value of RTD will be equal to 100 multiplied by 1 plus 0.00385 multiplied by T. Okay, and this value okay, and then 6 is the value of register or the value of RTD. Okay, next the voltage Vset, the voltage Vs, it will be okay equal to request multiplied by current, so here, and the voltage output in this case is from 0.2 volts to 0.36, and this is the 0.35, and we can check it. Okay, in this case we can see at 0 volt the value at 0 centigrade degree the value of voltage is like this. Okay, and when we increase it into 200 centigrade degrees, and then the value of current or the value of voltage we can check. Okay, this is the value, and here the result. It should be same. Okay, and as you can see, we have maximum and minimum value. Sorry. Okay, and then we can take calculation directly. And okay, the first one we can take calculation directly from VS pattern request, and that's we can have the IDC value. Value 1, it will be the value from equal to Vs multiplied by 1023 divided by 5 volt. 5 volt. Okay, and the value we reach in this case will be nearly 40. Divided by 5. Okay, nearly 40. And as you can see, the maximum indicates at 222, 72. And we can take the solution. Temperature resolution is equal to the temperature T max, value of T max minus T min divided by will be divided by uh, IDC mass minus IDC min. Okay, and the value in this case equal to 200 minus 0 divided by this one 27 uh, 72 minus request. Okay. Okay, and the release solution in this case is 6.25, and this case it means that it means that um, average okay average charge sorry 2022 okay it takes average charge in IDC value and that the step of the temperature is 6.25 around 600 degree. It means that when we change 6 degree and there is a change of the IDC value, and this is very inaccuracy. Okay, and then we can take a monitor here. Okay, and in this case, the current or voltage, and as you can see, at 200 Celsius degree, the value of IDC is only 72. And when we increase degree, as we can see, the value of temperature is 190, 99 is the same value, same, same. As you can see, when we change the temperature in the range of uh, around 6, there are no change in the IDC value. It means that the IDC cannot sensitive to the temperature. Okay, I did you continue, and uh, as you can see here, the value is not changed. Again, one more. Okay, let's check again. Maybe stop. Okay, there's value of sensor here. Okay, 90, 91. Okay, in this case it's 91. Okay, and I agree. Nothing changed. Nothing changed. Okay, and in this case, as you can see, when we change uh, 5 or 6 value of temperature and only one change of the uh, value of IDC. Okay, that is the first method, and that's in this case, if we take amplify for request, uh, when we take amplify, it means that in we not only uh, read the value, but also we have to uh, amplify so that we increase the sensitivity of the temperature. And how can we increase? The first one, we can take this one, more sensitive. I will take it to uh, high time. High time. This one means that 100 ohm. 100 ohm, and in this case, the current is 10 milliampere. 10, 10 milliampere. It's a little high, but no problem. Okay, and then in this case, it will be more sensitive. The next one, the current one is 0.01. And in this case, we can take a value of Vs. It will be this value, RTD multiplied by this one. Okay, it will be 1 volt, and the maximum will be 1 and 77, and the IDC2, it will be the oh no, okay, no problem. Okay, this can from this one to this one. Okay, from 20 and 4 to 377. In this case, the maximum is this one, 300 and this value. And then when we take this one, and then the sensitivity for 10 milliampere, in this case, it will be it will be uh, not this one, request 20 minus request. Okay. And in this case, uh, every strength of one over one sensor decrease, and then the current, the voltage, the value can detect change the value of IDC. This case is 0.01. Uh, and if we increase this one, it's okay. Uh, it will take more sensitivity, but in this case, it will take cell hitting on the sensor, cell hitting on the sensor, and it will cause the inaccuracy of the sensor element. Okay, but as you can see, when we increase the range, in this case, the range of measurement is only indicate the range of voltage is from 0.2 to this one, so that it will be very small. This one minus this one, and this is only 0.115, 0.15, so that it's a very small range in the IDC range. But in this case, it's a little high, Uh, okay, almost same. Okay, it's stick almost same, but range is maybe bigger. This is only 1.50, and this one is high time larger than this one. And if this one 5 times, and the resolution will be increased 5 times. Okay, that is the first and the second. Okay. Okay. And in this case, we have a conclusion. If Vs range is small, then the resolution will be I can check the raw or worse. What's bad? What's okay, I should not go. Okay. When we increase need to increase the range sensor, range of sensor to get the better resolution. Better resolution. Okay. The best ways is V mix equal 0 and V mix equal to 0 and V max equal to V is F. The best one is with using full range of IDC. Full range of IDC. If we use a little, and it will not good. Okay, as you can see, the range of temperature and the upper voltage. Okay, IDC, IDC, yeah. And it will have range from 0 to VIEF, and then it will scale it into the value of IDC value from 0 to 10 and 23. And if we use the small range, in this case, it's small like this, small one. Okay, and then it will have the IDC value is very small. And this is a useful range. And this one is useless. Useless. Okay. It means that we have a house with 5 floors. I have a house with 1, 2, 3, 4. Okay, we have 5 floors. But we only use frequency. No. We use this floor, and these 4 floors is empty, and this case we waste the abilities of the house. But if we use on of them, and in this case we increase the efficiency of the system or the house, and in this case is almost same. Okay, about the efficiency, if you using on of this house, and this is for rent, and if on, it will be okay, 5,000. But when you using only this one, and this one, no things, we don't use, and then only this one, and the maximum in the case is only 1,000. It means that we wait about 4,000. We need to chill on of request for the best efficiency. Okay, and that's the first one. Just takes amplifies. Okay. In this case, we have request and okay. First, we test amplifiers. It means that we amplify request the maximum value to 5 volt. Test some amplifiers, and then we gain when we take amplify. When we take amplify. Okay. Imagine that we have a request. Request. Okay, and then we can use abilities of voltage and ability of sensor. Okay, and if we take amplify, and when we amplify, I assume that we take a double, a double, a double, and we take double for this one, and this one will be double. Okay, this will double. Okay, and when we take amplify like this, the range that we use is increase. The first is using for U full for this one, and the second U full for this one is okay. And in this case, I will use the maximize for this one, the maximize position. Okay, and then we have again will be we divide by 3 months. Okay, and in this case, I assume that I using this one, this circuit, and again will be equal to 5 volt divided by 5 volt divided by this voltage value. Okay, and in this case, the gain is around 14. 14. Okay, and if I multiply amplify, and then the value in this case will be equal to this one, and multiply by this one. Okay. Okay, and in this case, if we amplify 14 times, the voltage at 0 centigrade degrees is 2.8, and the value of the voltage at 2 centigrade degree is equal. Okay, the minimum and the maximum range. And this case, the useful range is about 2.5, 2.1. But it's much better than this one. It's much better than this and this. And in this case, the resolution, it will be okay, and this will be okay. Let me take ADC first. Okay, the ADC value. Okay, the ADC value in this case, and it will be maximum value minus minimum value. Okay, And in this case, as you can see, uh, average chance of 0.40, 45, uh, and there is, and in this case the IDC will more as sensitive, uh, which will more sensitive than it will be more sensitive to the temperature, to temperature. Okay, and then the much this is sensitive and it will be much better than the other one. As you can see, the first one, the second one, and the third one. Okay, and then we can check it. Check this one. In this case, we will test amplifiers. Take amplify. Take the amplify for the voltage. Voltage. In this case, we can test amplify here. Uh, okay, the value 200. Okay, we will take again. Um, Stop. Okay, one more. Okay, and okay, and that we will have one of resistance, resistance here, 10 kilo ohm, and ground. Okay, ground here, and one more resistance, and here is the output, and the gas indicate if 14, 14, and I will set, I will set the register for this one is 130, and the gain indicate will be 14, 14. And again, we take a measurement. Okay, then we can check the voltage value. Oh. Wait for this. Okay, in this case, sorry, we take a current for 500, 1 milliampere, 2 milliampere. Okay, and here is the result of voltage. Okay, and its voltage is nearly required 4.9. 4.9. Okay, that is the value of voltage that we need to test. Uh, okay, and then we recalculate for IDC and the temperature indicate we can take the calculation for uh, request from the IDC from IDC value and the temperature calculation. It will be the value of IDC return to request. Okay, T is equal to T max and the value of IDC minus the IDC 0 divided by request. Okay, and in this case, I will retake calculation for X to check for the linear relationship equal to request IDC value. Okay, at first equal to the maximum temperature. Okay, maximum temperature minus minimum temperature minus uh, multiply by maximum minimum multiply by request by request. That is the value of IDC divided by okay. This is constant value, and this will be divided by uh, um, IDC max and IDC min. And this will be mass and means. Okay, and here is the result of okay, sorry, it will be okay. This one, okay, this one will be minus this one constant. Okay, that is the value, and here is the value of temperature that we take calculation from IDC value. And in this case, hence indicate hence. Okay, and here is some a little different because we take a round for IDC value because IDC is the integer value, not a double, so that we cannot take accuracy, much accuracy for temperature. Okay, and then here is the result of value of temperature that we can take calculation. Okay, and then as you can see the relationship is almost linear to the IDC value if we use the current source. Okay, and then after taking the one, we can apply into the IDC or the microcontroller. Okay, and this is the output of the amplified circuit. Okay, and then we will test programming for the microcontroller to take a calculation for temperature. Okay, and then reopen the code vision IVR. Okay, and we create a new project and using IT Mega. Okay, almost same to last week. We will config for IT Mega is like this one, the frequency, and then we open the UART and enable receive data and information that we set up in default with 9600 baud rate. And the second one is we enable the analog to IDC converter. Okay, the using of VCC as reference or the using the reference bits. Okay, and then we take a generation. Okay, and I will take this one. Pick for this where is okay. This will be for demo 4. Okay, that is the name. Okay. Okay, and then we can check again for the value. Okay, and at first we declare the IDC value, and we can take float for voltage, and for temperature. Okay, we have 3 watts, and then we at first we take the IDC first and indicate the IDC value but equal to this IDC. Okay, and in this case we will use the channel 1 and we test it out. Okay. Okay, and then IDC value equal to okay. And here is the IDC value. And we will take delay average 0.5 seconds. Okay, and then okay, then we first read the value of IDC first. Okay, let's go to protest demo and request. Okay, and then now we rush. Okay, again. Okay, we can take it again. Okay, and then the value of IDC is like request. Okay, from request we will take a value of context, the value of context. Okay, and then the value of context equal to equal to uh, IDC value. Okay, it will be multiplied by IDC multiplied by 5 volts divided by 1023. Okay, and I will voltage equal to okay. I will take print for loss. Okay, and this is voltage. And then we check first. Okay, and rest we can take a monitor. Okay, sorry. Check again. Okay, voltage. Okay, take a project configuration for take print the float value. We have to modify the print function with float and with and precision. Okay. Okay, and then review. Okay, then run again. Run again. Oh, nice. What happens? I don't know why when I build a firmware for your group, I make the topo for request. Why? This is the second time. Okay, I will check again. Release. No success. Oh, okay. What happened to request? Okay, so and then what happens? Why? Ross. Again. Let me check again. This. Okay, and that's why I miss again one more time. I miss non-varieties in the problem. Okay, and then the values. Wait. Okay, I will create one more time. Why? I don't know. When I present to this group, there is trouble when we export float value. Okay, IT mega 111 and big value. Okay, and enable UART. Okay, I will take a transmission and interrupt. Okay, and then analog. Okay, that is on for default. Okay, generate 76. Okay, Okay, and let I check again. Okay, value example. Okay, okay, I will check it. Okay, I will run again. Okay, request project config. Okay, we send this to plus. Okay, okay. Now it's displayed now. I don't know what happened, but sometimes they make text with capitalized. Okay, and then I will take a calculation for IDC and voltage and temperature. Okay, okay, and temperature. Okay, and then I will take one IDC value too. Equal to okay, the candle we reach is watts and voltage equal to voltage equal to uh, IDC value IDC value. Okay, um, multiply by 5 divide by 1032. Okay, and we can test IDC equal to and the value of voltage equal to okay. We take stick first. Okay, and then we have IDC value and voltage. Okay, then we run again. Wow. No. Hmm. Oh, why? Okay, I will take calculation again. What happened? One more time. Oh, what is the trouble? Why is take me text? Okay, so, and that's we will check it first. Okay, I will take stick one for deep value, and at first we take at the for context. Okay, then I check again. Okay, I convert this into linear integer value. We take integer first. Okay, and okay, so okay, but why? Okay, that's calculation. Okay, it's okay. But what happened? Why we push? Okay. Turn again. Okay. And then this is the value of voltage that we can reach from the IDC. We can take a calculation again, and we can check this. We can check it. Okay. Okay. This is the value on the protest, and this one is the value of the IDC that we reach. Okay. And then we will test more IDC. Okay. Okay, then IDC. Hmm. I don't know why it's error, but at first I'm using this, no problem. Okay. Okay, and then we take voltage. I will check it. Run again. Okay, it's running now. Okay, then we can take copies. Okay, IDC. Okay, this one will be double. No, and this will be IDC value. Okay, and that's run again. What happens? Oh, Okay, I don't know what happened. Okay, and then this is the IDC value and voltage that we reach from the uh, on the microcontroller. Okay, and as you can see, the value is almost same. Okay, and then we take a calculation for temperature, and then this temperature will be then we can take this value IDC. Okay, IDC minus IDC means we can consider here this value. This value that is the minimum 572. Okay, and in this case we will take a calculation G and G mass. Okay, equal to 200, 200, and then multiply by IDC value, IDC value minus minus 572, 572. Okay, this is the IDC uh, divide by the maximum in this case, maximum in this case we can check 1013, 1013 minus 500. Okay, this is the value of the temperature, and we can take more. Okay, okay, and this. Okay, and then we can display the result. The result. Okay, and then next we check the value of temperature. Okay, and here the value of temperature. Okay, and here is the result. Here is the result. Let's check again for request. For 56, 56, but request we have set reach at 25. Okay, no problem. There are little error here, but no. Okay, and then the error in the case is around 2 centigrade degrees. 2 centigrade degree. Maybe there is some of error when we take the amplifiers for a circuit. Okay, and then we take a reduce for a value of temperature. Okay, and as you can see, when we take a reduce, the value will be like this. Okay, and let's check again. For 200, we can take the value of this is 1009. Okay, and I will recalculate for this one. 1009. 1009. Okay, then check again. Okay, run again. Okay, and as you can see now the value is 200 now. Okay, and then we reduce check for changing. Okay, here is the changes of the value of temperature. Okay, then reduce more. Okay, here the result. Now, okay, and then we take reduce to 120. Okay, 51. Okay, the need to reduce it? No. Okay, and we check again for the minimum. Okay. Hmm? What happens? I don't know why. Okay, and then here the result. Okay, but why is it difficult in this case? I don't know why. Software price. Why? Okay, and as you can see, the value in this case is 574. Okay, I check it. Okay, and then it will make more accuracy. Okay, let us. I don't. Nice. Okay. Okay, and then this is circus that we have a bill and the IDC. Okay, and then we increase this. Some that 59, 59. Okay, and then we check the voltage that we can reach from the IDC. Okay, and in this case, we have reached the temperature like this, and there a little error. A little error. I think no problem. Okay, we can accept it. Okay, and then we have text a demo for reach the temperature and calculate the temperature from the real sugars, and there are some of calculation. And in this case, when we use the current source with constant current, and then we can take a linear relationship for a value of temperature. Okay, and that's you can take a repeat for this exercise, this demonstration. Okay. Uh, for this demonstration, do you have any question or any trouble when solving reading the sensor signal? Right. No. Okay. And that's the homework is takes a calculation for the temperature and evaluation for accuracy of the circuit. Okay. Okay. The homework is not very difficult. In this case, we reach temperature from volcano. Okay, decide and reach temperature from volcano. Okay. And we have one more in our class. I have you one day. Okay, we have one day treatment and for TH. Yeah. Um. Okay. 48 we divide because we have around we have 45% so that we need to divide into two groups and we will okay and the days how about your free time okay then we can test for next day our next Thursday and Friday from 8 a.m. Okay, this is for first group and second group. Okay, in this case maybe we method this and okay and the remaining days I will talk about exam and if you take a review for the course and uh, you can add me for any problem and for TID we take a practicing some device and instrumentation in lab and the next is the project final project. Okay, we will discuss okay and how about the remember I will okay this one I will take the schedule later. Okay, is there any trouble with the TID guys?
Em ơn phí một tí mà.
Từ từ đi. Okay, final project work in group. Okay, any further question, guys? Hmm? Okay, software. It should be some. and sometimes visual. Okay, which is Netflix. And the final project will be take after. Okay, it's okay for you. Okay, and then I will take the evaluation for the final project at the end of final exam. Okay, it's clear.
Yes.
Okay, good. Any further question? Okay, and then take a review for the sensor. Okay, and this one. Okay, and the second one is design the circuit. Uh, multiple. Okay, you can use KC and ARM for your project. Some case of making. For what choice?
I would like to know if you can give us some criteria for the marking, like the checkpoint that we should have done something. Like like I want to know the score
Sorry, I cannot
parameters.
hear you.
Uh, I want to know that if you can give us like
Okay, about okay the homework. Okay, CVP is the average. Some. Okay, it means that average or not. Okay, okay, I will take summarize on of your homework and take average of terms. And the second one for the okay TID on the TI result. Okay, and okay, okay, and uh, uh, some of exercise, exercise in TI. Okay, and next week will be for I will take it for lab. Lab. Okay. Okay. In this case, please note that which lab uh, column if you are absent, and there will be there's maybe upside points, and then it cannot take a sum for all of your points in our class. And next one is final project. Okay, and this is and next one is final exam. Okay, in final exam, about the final exam, I will have some of question review of sensor and instrumentation. Instrument is automation, and I will add some okay PLC programming, uh, some of symbol. Okay, and then we have some of uh, calculation, circuit design for sensor signal processing. Okay, and in this case, we will have for such as load cell, uh, thermocouple, okay, temperature, encoder, okay. Okay, that is some of men's boys is our course. That is result from your homework. Okay, and try the TIs and finish the exercise and take evaluation. And for final project, I will take it into lab, maybe into the lab. Okay, in this case for midterm, okay. Final project and uh, test and test your test will be in midterm. Okay, about the homework. Okay, you can present me on the TID. Okay. Any further question, guys? Okay, it's clear.
Yes.
Okay, and that's how. If you clear us, then we can finish now. Okay. Uh, okay, I will arrange for the reminders of letter, and I will announce to class for this. Maybe in next week. In next week. Okay. About the TI tab, uh, we will have a TI day for the first TI is on Thursdays and Friday, and the second is from maybe from end of uh, end of Christmas. Oh no, Christmas. Okay, okay. It means that after this one we have 1 week off, and at the end of this month we will have one more TI day, and then we will review for the midterm test or final exam. Okay, then we stop now and see you.